This is Kosmographia, the Randall Carlson podcast. Welcome back, ladies and gentlemen, to Kosmographia, the Randall Carlson podcast. I'm Russ. This is my brother Kyle.
How's it going?
And we are joined, as always, by Bradley and Mike. Mike is in Georgia. Brad, you're in North Carolina again, right?
I am. Returned home. Yep.
Returned home from all the trips. And, of course, Randall, star of the show, talent. How you doing, buddy? How's it going over there?
Hey, I'm doing really well, man.
Yeah?
Really doing good, yep.
Yep. So I know we talked about this last episode, but we just finished a whole bunch of trips and we're planning a whole bunch more. So
it's true.
Yeah. Before we get into all the topics, I think we should briefly mention at the beginning of this show, you know, what's in the works, for the future. Like you guys have the Cumberland tour coming up, right?
Mm-hmm.
And the dates are the month of that. What is it? Is it in November of this year?
Well, I think Rowan, my brother, who's kind of heading that up, I think he's got it working it for November.
Yeah. Okay.
It should be the first week in November.
First week in November.
For 5 days.
Yeah, which will be a nice time of year because I think we'll just be getting into the leaves coming down, so we'll be able to start seeing some of the landscape.
Yeah. That's
quite normally hidden from view.
Right.
And, you know, what's interesting is that, of course, you know, during the winter months, that's typically... You know, I mean, there's still travelers and tourists and things, but they usually don't get off the beaten path too much. Some do, of course, but, you know, most travelers will be going right by places without knowing that, you know, something is there. So this is about showing that underneath the canopy of forests in the southeast, there's a landscape, a huge vast landscape of catastrophe.
Right. Excellent.
Mm-hmm.
And we also have another Scablands trip coming up.
In September.
That's right. Of this year.
Of this year, yes, this year.
So it's going to be the other end of the year. We did the first one in spring, and we're going to do this one in fall. I think we're adding a day. We're going to be hitting more spots, going a little farther out. It's going to be a lot of fun.
We're going to do a little bit more relaxed pace with that extra day.
That's right.
But hitting more spots.
Yep.
We'll be staying in the same resort complex at the south end of Soap Lake.
That's right.
Did we like that? That was a nice place, wasn't it?
It was a very nice place.
Good place to base out of. Excellent.
Great place to base out of. Yep, absolutely.
Yep.
Yeah, Darren Grimes is the prime mover behind this, just like the previous one.
Yep.
And we hope that by September, there's not going to be any border crossing issues anymore.
Right. That's right.
We certainly do.
So his
which made it hard on Darren.
Graham will be with him. So he missed the one in the spring. So he'll be able to come down and go with us. Yeah. We're going to see quite a few different sites than we did. So we're going to hit the major ones. But there will be a lot of new sites. There's so much to cover. We're gonna shake it up and be different on this one.
Mm-hmm.
So even if you came to the last one, half of it at least would be new.
Yeah, there'll be some overlap because some of the places, Potholes, Cataract, Dry Falls, Steamboat Rock are kind of necessities.
Yeah,
definitely.
And I can't imagine being at Soap Lake without taking a cruise up the Coulee and, you know, hitting all those spots.
Yeah.
But, you know, we didn't do Boulder Park. We didn't do the Great Bend area. We didn't do Alula Gap last May. So,
yeah.
Those
are on the new list.
Yep.
Uh-huh.
And even just the driving, it was phenomenal. I mean, I'll never forget driving down into Moses Coulee. That was absolutely beautiful. And then also Devil's Canyon.
Devil's Canyon is impressive as hell.
Yes.
Yeah.
It was really striking.
And when you understand the sequence of events that created it, that's a big part of it.
Yeah.
I mean, it's impressive. Yeah, you go down the highway there and you get to the bottom of it, but then you realize that this was a spillway. It was an overspill. It was
an overspill, yeah.
An overspill right over the ridge, and it cut that canyon down. Now, the question is, how many separate flows were responsible for the ultimate deepening of that canyon? That's the question. Was it one? Was it multiple? Was it more than one? If it was more than one, how many more?
Yeah.
You know, there's a lot of unanswered questions about this phenomenon, and that's part of what we're doing. It's not just sightseeing. It's also about unraveling the mystery of what created these extraordinary landscapes.
That's right. And it also, I know I've said this before on this show, but it's really struck me that there was no, underfit canyon or river inside the thing. That really shows you that it was just only enormous flows going through there that cut that thing. You know, there's no secondary or permanent water source there now.
Right.
There's no river or stream or anything in the bottom of that thing.
Right.
And, that really struck me because it's like, it's rare that you would drive through a canyon and you don't see signs of smaller water flows at the bottom, continuing to work on the thing. It was just, all it was catastrophic, and then it stopped.
And then it stopped, yes. Yeah. And then it's interesting to compare it to Palouse Canyon, because Palouse Canyon has the river in it.
That's right.
But they were both created by the same processes, overflows that then cut down through the ridge. The Palouse Canyon, though, further east, caught that water coming down from the northeast. Yeah. And once it captured that, it diverted it south. And at that point, the water flowing through Devil's Canyon stopped, if that makes sense.
Yeah, that's right. The water level drops low enough and that flow quits. That flow stops.
Yep. So
what are we looking at today? Where are we going from last week's show?
We're going to continue to unravel the landscapes. I mean, there's so much more to learn, but we're going to also be talking about the phenomena of outburst floods, which in Icelandic the term is Jökulhlaups, which basically means outburst floods. Outburst lakes. These are lakes that are dammed by glacial ice. The formation of the lakes can occur by several means. They can be a basin being filled by precipitation. They can also form as a result of subglacial volcanic activity, such as we find in Iceland, where some of those catastrophic outburst floods are caused by Vatnajökull, if I'm pronouncing it correctly, which I'm probably not. But there will be, every 5 to 10 years, there will be an eruption that causes a reservoir of meltwater to form under the ice sheet. And typically what it does is, as the water mass increases, so does the pressure, and it eventually forces its way through the ice. It finds usually a subglacial tunnel, and then discharges to the south in the form of an outburst flood. Typically from the reservoir to the margin of the ice sheet where the outburst occurs is around 30 miles. Which I find to be interesting because we've been talking about the Purcell Trench lobe of the ice sheet, the Cordilleran ice sheet, blocking off the Clark Fork River. And then by looking at the maps and going from the point of interface between the lake, which is, the arm of the lake, and I'm using the terminology now for the orthodox model of this thing, right? Just for convenience sake. The water is pooling against the ice dam right there east of Lake Pend d'Oreille, right about roughly at the Idaho-Montana state line. Now, from that point to the snout of the Purcell Trench lobe, depending on where you put it, is going to be between 25 and 40 miles. So it's pretty much right in the same ballpark distance as the drainage of the subglacial volcanically produced reservoir up in Iceland. Now, typically, the timing between the eruption of a volcano under the ice sheet, in Iceland, it's actually an ice cap. The timing between that and its final emergence from the snout of the glacier is typically a couple of weeks to travel at 30 miles. And then once it bursts out, it's now created a very effective conduit. Initially, what it will do is it will exploit any weakness in the ice, any fracture line, any means of egress into the ice. And of course, as the water mass increases, so does the pressure. Now, this is a subglacial pooling of water, right? So as the eruption proceeds and causes the melting of the ice, now you get more water. The water creates pressure, which sooner or later some threshold is breached, and the water is able to percolate through the ice and create a discharge conduit to the perimeter of the ice sheet. And that's basically then what happens. I think in the case of the Icelandic outburst floods, it's usually a flood that's between the base of the glacier and the substrate or the ground beneath, which is typically, of course, going to be glacial till, which is mostly going to be porous material. So, the idea is to look at some of the outstanding examples of modern outburst floods, and see what we can learn from those that might help us understand the much greater ancient floods like the so-called Missoula flood or the Bonneville flood. Of course, the big difference now between the Bonneville flood, which we talked about in an earlier episode, which came up out of Utah ultimately, was that the Bonneville flood was a lake held in by a sedimentary dam of porous rock, and Lake Missoula was held in by ice. Now, in the case of Bonneville, once it overtopped the sill, the sedimentary rock sill that was lying on top, the sedimentary plug that was lying on top of a granite sill, once it started spilling over, it rapidly began to eat its way down, probably initially slow at first. Depends on how fast the lake water came up, right? So this is a question, did it come up over a period of years, decades, or was it perhaps months or even weeks? Now, and that's part of the question about the origin of the Bonneville floods, because, they were the overflow of this massive lake in Utah, Lake Bonneville, which had its counterpart in western Montana in the form of Lake Missoula. But again, the difference was Lake Missoula is up there contiguous to the ice sheet, right? And it was an glacial ice dam that held it in. Bonneville was held in by this sedimentary rock. So we can picture now whether it took a matter of 3 or 4 days or whether it took several years or somewhere in between, the process is going to be the same. It's just going to be the rate at which this process takes place. The water level rises and it begins to flow over where the water flowed out, what is called Red Rock Pass now, is right up there as you get northern Utah and then you get to southern Idaho. There's that whole valley in there. Red Rock Pass is like the lowest point within the whole margin of this huge inland sea called Lake Bonneville. So that was the lowest point. So as the water level rises, that will be the first point that the water begins to spill over, if that makes sense. So now the water begins to spill over and it's flowing. If it was a slower rise in the lake, then presumably what's happening is there's a river flowing out of it. On the northern end, the river is flowing north, flowing through ultimately into and connecting with the pre-flood Snake River. Now, if it's a fast rising, then it's going to be a much more fast down cutting. And of course, I'm tending to believe that the whole process was fast. And so the lake level rose probably as a result of some series of extreme pluvial events, pluvial meaning rainfall, right? Water rises, spills over the col, C-O-L, which is the same as the saddle. It's a softer rock. The shear forces of the water quickly erode that rock down about 300 feet. At 300-foot depth, it's swept out the softer sedimentary rock, and now there's a hard granitic or granite sill. At that point, the flood stops, and it stabilizes at that elevation. And you can actually see around the lake basin, the two shorelines that are separated by about 300 feet. The high water mark, when it first spilled over, and then where it stabilized, 300 feet lower. Now, once it stabilized behind that granite dam, the outflow was over. And then, because of the fact that this flooding is taking place right at the end of the Ice Age, and again, we don't know the exact timing, but it would be very important and useful to know this, in the immediate post-flood, Bonneville flood environment, it's radically different now. So where there had been copious rainfall before, now we're basically moving into a time of aridity and becoming much more desert-like. So now what's happening is you've got this big bathtub full of water, right? The spigot has been closed. Its outlet, it's eroded its way down. It's now stabilized at the granite sill. And from that point on, the water level just starts dropping as the ratio between evaporation and precipitation shifts onto the side of evaporation.
But that's not supposed to have happened to Missoula, right? Once the ice dam breaks, all the water is supposed to have escaped that basin.
All the water, because if you look at the floor of Lake Missoula, even the distal reservoirs like the Bitterroot Valley or the Mission Valley up near the Flathead Lobe, they're all sloping towards Lake Pend d'Oreille.
Right.
See? So, yeah, once there's no ice dam to obstruct the outer flow, then all that water is going to drain. Although, again, it's not a completely smooth topographic profile. So there's going to be low points that are going to be holding water probably for centuries before it finally evaporates away. And, of course, the deeper basins like Lake Pend d'Oreille and Lake Flathead are perennial lakes.
So how big are the lakes that happen with these modern outburst floods? I mean, like, do they get big enough for people to actually call them lakes? How long do they last?
Well, Russ, that's a damn good question.
All right, great.
We can certainly get into that. In fact, I had intended to get into that.
Excellent.
Because we can learn some things.
I'm just wondering, like, how much. What is the scaling here? Because I know you've talked about how we have these modern outburst floods, and geologists are, these people are considering, well, if we just scale that way up, we have Missoula. But is that really true?
Yeah, I mean that's what. I read that quote. Couple of quotes last episode, didn't I?
Yeah, what I mean is it really true that you can just scale up modern events to fit what they think happened with Missoula? Like, would that actually work?
Would that actually work?
Yeah.
Yeah, well, that's kind of what I was wondering.
All right.
So we've talked about we've talked about Moses Coulee. You just, in our introductory discussion tonight, you talked about how impressive it was going into Moses Coulee. So the first paper I will read from will be Larry Gene Hansen's PhD thesis that he did on Moses Coulee back in 1970. Okay, so we will just do a share screen here so people can see what we're talking about. Here's mighty Moses Coulee. I'm tracing it out with my cursor. It does this dog leg to the west and then comes on down. So there's, just like with Grand Coulee over here, there's an upper and a lower Coulee. Moses Coulee has an upper and a lower Coulee. And in fact, if we zoom in, there's a number of cataracts and steamboat rock type formations right here that show up quite impressively on the digital map here. Just like if we zoom over here to Grand Coulee, we see the Great Cataract Complex. We see very much the same type of formations, spillway channels that are now basically abandoned, extinct cataracts like you see right here. So Moses Coulee, very similar, but what we see here is that Moses Coulee starts this down cutting right in here. And if we follow this up, to 172, right in here after Mansfield, if you guys remember, let's see if it even shows. I wonder if it'll show up on this map. Let's go to here. Let's see. This might be it right here. Let's see.
Yeah, I think that's it.
I think this is it right here. Jaeger Rock.
Yes. Oh, yeah.
There it is, Jaeger Rock. Look, I was looking to see if we could see us there next to it, but I... Okay, so watch now. If I zoom out, do you see the connection, the strategic position of Jaeger Rock relative to where the down cutting starts, the erosion starts, that ultimately channelizes and becomes Moses Coulee? I've talked about this process repeatedly, and even notice here, it's drumlinized.
That's what I was going to say. There's a northwestern-ish shape to the drumlin features there.
Yeah. Yes. So here's what I would speculate. Now, if I back out, you can very clearly see the arc of the Withrow moraine.
Yeah.
So this is the Okanogan Lobe coming up like this, probably encompassing what is now Upper Grand Coulee. And if we take this lobe right back up to where it meets the Columbia Lobe coming down here, right there at that point where those two lobes join is where Grand Coulee Dam is, which is interesting. We actually went to Crown Point. We went to this point. Do you remember that?
Yeah. Yep, I do.
So from this vantage point, we could look over at the dam and we could see the Great Notch, which is the head of Grand Coulee. Now, the conventional explanation is that the water that created Grand Coulee came from way over here. This is where the water came from. And it traveled through what is now the basin of Lake Pend Oreille, down through Rathdrum Prairie, which is this, down through the Spokane Valley, which is this, and whatever water was not diverted to the south, creating Cheney Palouse, then flowed to the west through what is now the Spokane River Valley. And now there's evidence that there was a massive pooling of water in the Spokane River Valley. Well, this has been named Glacial Lake Columbia. I have some critical thoughts about the existence of Glacial Lake Columbia, the same kind of thoughts I have about Lake, and I'll put that in air quotes, Lake Missoula, Lake Columbia. But in any case, Spokane River comes across here, meets the Columbia right here. And so the idea is that at some point there was this glacial lake here, basically lapping at the toe of the ice dam that filled the Spokane Valley. At the same time, you got Lake Missoula, 2,100 feet deep, pressing up against the ice dam up here to the east of Lake Pend Oreille, somewhere around Cabinet Gorge Dam, which is near the Montana-Idaho state line, which is that dashed line right there. So to create Grand Coulee, we've got to get the water out of Clark Fork Valley and get it across here, and it's got to also bypass the Telford Scabland tract, which is this. And then it's got to get over here and breach the ridge, which is about 2,400 feet above sea level, cut this down, and then flow. Now it's diverting south through here. The idea is that the Okanogan Lobe was here. The water came from the east and hit the Okanogan Lobe and got diverted south. And that's what created Grand Coulee. So in order for Grand Coulee to occur, the Okanogan Lobe has to be here. Because if the Okanogan Lobe isn't there, then why would the flood spill over this sill and not just follow the pre-existing Columbia Valley down this way. See? So in order for the water to be deflected to the south, all of this has to be dammed. I, however, would propose an alternate explanation. Picture you've got a lobe of ice coming here, and you've got a lobe of ice coming here. Where they meet, that area would be called the interlobate zone. Now, that interlobate zone is going to be a trough because both of these lobes are going to be domed, right? You've got a mountain range here. The ice is going to be filling the Sandpoil River here, and then it's going to be doming over the mountains here, and then you're going to have a trough over here, right, between the two lobes. And what I'm suggesting is we should consider that rather than the water coming from the east, way over here out of Montana, it's coming from the north. Now, we can explain Grand Coulee by saying that the Okanogan Lobe is already here. But how do we explain Moses Coulee? You can see we run into some problems there because Moses Coulee, as you saw, is a huge feature in the landscape. It's a massive valley. It's 900 feet deep and over a mile wide. So you're talking about a couple of 100 million, 200, 300, maybe 400 million cubic feet per second flowing through here, right? Now we can trace a totally conspicuous, obvious channel up this way, follow it to the north, and what we see here is the classic, typical process where you have a sheet flood exploiting a zone of weakness and then becoming channelized. And if we follow Moses Coulee right up to its head, this is what we see. We see evidence of subglacial sheet floods right here, right there, with those drumlins, rock drumlins, right? And then we can see right here how the water is becoming channelized. And once it becomes channelized, that's when it accelerates the down cutting. And so I look at this and I go, no, it sure does seem to me that we don't need water coming all the way from western Montana. But you see, that creates a complication. Like if it's not coming from Lake Missoula, where's it coming from? Well, I think we can go right on up where Brad and I and Jerome Lessman went a few years ago. And if we go up to the Omak Plateau, we see the same type of landscapes and erosion caused by high pressurized subglacial floods. So, I mean, all of this is scabland type erosion, and we can see channelization here, right? So when we zoom out, all of this water, now picture this. You've got this lobe of, all of this is under ice, right? So you've got subglacial floods coming down this way. Look at Omak Lake. Look at the topography around Omak Lake as we come south. See, this was once upon a time a much earlier valley or channel for Missoula, because at one time, I'm sorry, not Missoula, Columbia. The Columbia River, here's its original channel going to the north. You see this? So what it did was the original Columbia River skirted right around the northern tongue, because what this is basalt in here. And this was the northernmost extrusion of the basalt lobe or basalt tongue. So somewhere between probably 6 and 10 million years ago, all of this basalt flowed from the south. And when it did that, it blocked the original flow of the Columbia, forcing the Columbia to divert north and go around this tongue of basalt and come down this way. Now, when the ice sheet came from the north, it blocked it from the north. So you picture the ice sheet is coming down here, blocking the northward flow of the Columbia right here, forcing the Columbia to cross-cut right across the basalt. Is that making sense? It's a protracted sequence, but the final stage of this would be when the ice came down and prevented the Columbia. You can see here where it turned north. When this valley filled with ice, this didn't turn north. It came across. So at some stage, the ice was probably the margin was right here, and the Columbia River flowed along the southern margin of the ice sheet. And this could have been a much earlier. I mean, this might have been an ice age 50 or 100,000 years ago or longer, right? Now, once that downcutting has occurred, you have a deep valley here, right? Now, the Cordilleran ice sheet comes along around 18,000 years ago, comes from the north, comes across, completely fills the Columbia Valley here, where you see Bridgeport, where you see Brandt's Landing, completely fills that, and then continues all the way down until it reaches what is now the Withrow Moraine, right? So that's the sequence of events. Now, I'm going to go to Larry Gene Hansen on the origin and development of Moses Coulee and other Scabland features on the Waterville Plateau. This is an unpublished PhD thesis at the University of Washington. So on our first trip, Brad and I went to the University of Washington so that I was able to get a copy of Larry Gene Hansen's PhD thesis, which is not published anywhere. So this is what Larry has to say. The ancestral Columbia River was diverted onto the Columbia Plateau at least several times in the Pleistocene. That's what I was just talking about, right? Where it was diverted across the basalt. Such a diversion by the Okanogan Lobe during the Withrow advance is clearly documented. Other diversions onto the plateau probably have been affected by glacial blockades of the Columbia Valley by earlier advances of the Okanogan and Spokane lobes. During the catastrophic release of meltwater from a large glacial lake within the system, water may have flooded onto the plateau. Now get this, not with the aid of a glacier dam, but from the mechanism of hydraulic damming of iceberg jamming in Columbia Valley constrictions. Now, if you think about what was just said there, that opens the door to a completely different interpretation of this whole phenomena. You see, he's saying, because where's the ice dam? You see, I mean, again, picture that. Where is the ice dam? You know, yeah, you can theorize that there was an ice dam up by Lake Pend Oreille, but if you don't accept that the water creating Moses Coulee came from the Clark Fork Valley, and you look back at that map we were just looking at, where's the ice dam? Right? Okay, so now he goes on to say, which I find to be very interesting. The Pleistocene, quote-unquote, Spokane floods, outbursts from glacial Lake Missoula, North Idaho and Northwest Montana, are the most intense floods known from the geological record. The maximum volume of impounded water was approximately 2,184 cubic kilometers. And it's actually now known to be bigger than that. This is 19, let's see. Okay, actually, I'm not reading from Larry Gene Hansen anymore. I'm reading from Clark, Matthews, and Pack from 1984, Outburst Floods from Glacial Lake Missoula. Excuse me. So given that that's 1984, yeah, that is a little bit bigger. Glacial Lake Missoula differs from most ice-dammed lakes so far investigated in several respects. The water volume is 3 orders of magnitude greater than for any modern ice-dammed lake, and the ratio of water volume to reservoir depth is much greater than for modern lakes. A major extrapolation of data from present experience is thus called for. And then I read the quote, which would be worth revisiting from geologist David Alt in his book, Glacial Lake Missoula and Its Humongous Floods, 2001, when he says it is surprising that no one has found fossils in Glacial Lake Missoula. No petrified wood, no leaves, no bones. We have no tangible record of the plants and animals that lived in Glacial Lake Missoula or around its shores. It is especially surprising to find evidence of a great lake with no sign of fish, not even a few scattered scales. All the shorelines are very faint. Nothing suggests the violent crash of breaking waves. Trenches dug through Glacial Lake Missoula shorelines reveal precious little that looks like what we see in a trench dug through a modern beach. The lake shorelines show hardly a trace of wave depositions, hardly a pebble that the shuffling waves worked to a flattened shape, nor do the old lake shores include such common features as cliff, sand spits, or deltas. So that, to me, is pretty damning to the whole lake model. Because if, in fact, it's only a temporary ponding, that's a temporary feature in the whole process of this massive meltwater event, then you wouldn't expect there to be the normal lake deposition. If, on the other hand, there was a body of water repeatedly filling and emptying, nonetheless, there should be evidence of all kinds of if the lake is there for 100 years, well, there should be a pretty distinct shoreline carved in 100 years. There would be fossils found within that lake. Within 50 years, there would be fossils found within it. There would be evidence of some kind of, freshwater vegetation, mollusks, shells of some kind. But it's not there. But the water was clearly there. It left its traces up to 4,200 feet above sea level. So that's what I'm getting at here is that, when we begin to look at this thing, the conventional scenario just seems to sort of unravel. So I actually had another quote from Larry, but I seem to have misplaced it, so I'll probably find it after the break.
All right.
But so Brad and I saw on one of our trips, we cruised up the Columbia. Let's go back to the map. And all right. So what we did is we went up to Kettle Falls and we traveled this route down. This is 25. Followed this route down Lake Franklin, which is actually just the Columbia River, looking at features along here with the idea in mind that there was a connection between subglacial flows and perhaps proglacial flows coming down the Columbia Valley and discharging here by Telford and Creston, and actually that the Telford Scabland tract was formed by water coming from the north down what is now the Columbia River Valley instead of coming out of the Clark Fork over here. So what we found, and I don't have pictures of it handy, but we can look at some next week, was all along here there are deposits, huge sedimentary deposits with foreset bedding dipping south. Now, subsequent to that excursion of ours, which I don't even remember the year of it, there was published in 2003, we find at the Seattle annual meeting of the Geological Society of America, we find a paper was presented by E. Kirsten Peters with the Geology Department at Washington State University. The title of the paper was Evidence for 2 Outburst Floods of Non-Missoula Origin in Northeast Washington State. Got that? Non-Missoula origin. So here, I believe Kirsten Peters, I believe, is a woman. Not 100% sure, but anyways, I think so. So she says previously unreported and large scale, 55 meters high and at least a kilometer long. 55 is that's about 180 feet. So that's pretty thick deposits. Now visualize along the river, that stretch, that reach of the river there where we were just looking, that north-south reach of the Columbia River, which presumably at the late glacial maximum was filled with glacial ice. There are large-scale, four-set, boulder-rich gravel beds of Pleistocene age, 180 feet high and a kilometer long. Now, the main exposure is south of Kettle Falls, Washington, along the shores of Lake Roosevelt. The four sets dip about 28 degrees toward the south, in keeping with outburst flooding from, get this, from British Columbia. Most of the gravels are matrix supported. Clasts in the beds include intermediate porphyritic volcanics, granitics, quartzite gneiss, slate, and conglomerate. Outburst flooding from North Idaho down the Pend Oreille River into the Columbia above the international border is possible, as is outburst flooding directly from glacial meltwater in BC itself. So yeah. Now, then the paper goes on. Large-scale four-set beds of boulder-rich gravels also lie in the lower Spokane Valley along the Spokane arm of Lake Roosevelt. Their outcrop is 4 kilometers long and at least 15 meters high. Boulders range up to 1.5 meters in diameter. So that is right at 5 feet in diameter. So you've got, a mix of sedimentary sizes, but entrained within the sedimentary matrix are boulders that are up to 5 feet in diameter, suggesting ice drop deposition. So in other words, boulders that are being carried aboard icebergs. And then those icebergs are being swept along and melting and dropping their boulders. Clasts, C-L-A-S-T-S, clasts, which are the pieces of sedimentary material. Clasts are dominated by granitics, but also include quartzites, intermediate porphyritic volcanics, and basalts. Belt series rocks, suggestive of Lake Missoula, are notably rare. The boulder-rich gravel four-sets dip down valley toward the west. Source of the outburst flood responsible for the beds may be from the northeast. Now get this, down the Purcell Trench in northern Idaho and across the Lake Coeur d'Alene area. Stratigraphically above the four-set beds are multiple horizontal but strongly cross-bedded beds of dark basalt-rich sands. The basalt sands are interbedded with light beds of lacustrine fines, meaning fine sediments of lake origin. These latter two bed types are consistent with outburst flooding from glacial Lake Missoula. Okay, so let's go back to the map so that we can get this picture here.
Let me interject something just for a second there, Randall, just to eliminate any confusion. You've called it Lake Franklin several times, and in that writing, it's Lake Roosevelt. So the lake backed up behind Grand Coulee Dam is Lake Franklin D. Roosevelt. So
thank you, Brad.
It's the same lake, but yeah, you were calling it Franklin and they called it Roosevelt. So it's really the same lake.
Same lake.
Backs up the Columbia River behind Grand Coulee Dam. Yeah.
Right. I'll zoom in. So here's the modern Columbia, and here's above the dam is the actual lake, Lake Roosevelt. And the reach that we were talking about in this paper I was just reading from is just below Kettle Falls up here. And the author of this paper is saying that it was of non-Lake Missoula origin, that it came from meltwater, British Columbia. Which paper was in 2003. When we went there in 98, did our first excursion across the Scablands in 98, and that was followed the next year by our first trip up into British Columbia in 1999, where we were looking for evidence that the floods that at least created Grand Coulee, Telford, and Moses Coulee actually came from British Columbia and not western Montana. So this work by this geologist here supports the notion, because I think, like I said, I think it's a woman. I apologize if it's not, but that report is this area right here. And the foresets are dipping to the south. Like I said, we're 180 meter thick, a kilometer long deposit. Now that is suggestive of a very substantial flow of water. Was it subglacial, or was it a later stage when the ice was melting away? At this point, I don't know. But clearly,
like that was, and I don't remember you reading this a minute ago, but it seems like it was 28 degrees.
Yeah,
so that's pretty steep. Yeah, showing a good flow.
Yes. So that's a pretty swiftly moving, vigorous flow of water, sediment-laden water coming to the south. And I would argue that those beds up there are related to flows that discharged right here and spilled out over the Scablands and formed the Telford.
And she was saying that there was some stuff in there that was consistent with with Missoula. Did she
over
say that?
Here in the Spokane Valley.
Okay.
Over here. That's what I was going to get to.
Yeah.
Which, of course, could be, because look, if you look at this,
right,
water came down this way and undoubtedly split at this point. Some flowed south, creating Cheney Palouse here, and some flowed to the northwest, creating all of this stuff that we see here.
Yeah, okay. That makes sense. I was like, how did she find
lacustrine
sediments up in that trench?
That's what I was wondering too.
Well, right. She was saying that there weren't any in the Spokane Valley up in the other valley.
Yeah.
Right.
Now, the only other thing I'm a little bit confused on was the path of the river that you were talking about. You talked about how the basalt flow sent it to the north, and then when the ice sheet came down, it sent it back to the south. But what happens when you have the Okanogan Lobe coming all the way down?
Yeah,
where was it going then?
Where was the water going then? For the Columbia
River.
Well, think about this. Let's go back to the map.
Did it go subglacial?
Let's go back to the map. And that's a good question. I'm glad you asked that. So
we do need to be considering break time too.
Yep, it's about break.
Well, tell us in the break. Keep everybody else.
That's right. Yeah, tell us in the break. Audience doesn't need to know this answer.
Okay, so
but yeah, the ice is covering. Well, you're going to show it, but yeah.
Well, yeah, the ice is coming. Look, here's the Columbia River now. There is no Columbia River.
Okay,
right.
That's the whole point. There is no Columbia River.
There is no Columbia River.
There's no river. All right.
Right.
Got it.
All right. So on that note, let's take a little break, and we'll come back and we'll continue unraveling this mystery.
Excellent.
Okay.
And welcome back, everybody. Yoga Laps coming soon. Promise. To a podcast near you. Before we get into that, really quick, I wanted to mention, check out randallcarlson.com if you want to look into any of the merchandise or the tours. There's, the compasses, T-shirts, hats, the platonic solids, all for sale there on the website. And then, of course, information about the tours and all of that, as we mentioned before. And also want to mention our good buddies cbdfromthegods.com. If you're interested in any of their products, go to cbdfromthegods.com, put in RC ships free if you order anything, and you'll get free shipping.
I will just throw in one quick thing about CBD from the gods, and that is that I keep finding new uses for it. So over the last couple of weeks, I've had off and on episodes of my left ear feeling somewhat pressure and kind of itchy, but it might have something to do with I tend to sleep on my left side. I don't know if that has anything to do with it. But about a month ago, I started feeling this pressure in my ear, almost like the kind of pressure you feel, when you're coming in, landing in you've been riding in an airplane, but that kind of almost with kind of an itchy feeling, So I've been going for about 3 weeks, and finally, a couple of weeks ago, I had Julie. I said, Julie, I've got an idea. I want to try something. I'm going to lay on the side. I want you to put a drop of CBD oil in my ear. So I laid there. She put one drop, went into my ear canal, and pretty much the next day, pressure gone, itching gone. So,
wow.
Yeah.
Do it for science, folks.
That's right.
Yeah. So, yeah, I'm not sure what happened there, and it could just all be a coincidence, but no, it had been like, for 3 weeks, I'm going like this, going, what the hell is going on with my ear? Another little, a little symptom of living on a planet.
Probably better than a spacesuit.
That's right.
Probably better. But yeah, so I wanted to report that. We put a drop of CBD oil in my ear, and whatever was going on with my ear, it seemed to have knocked it out. So anyways, yeah. I think CBD is good stuff. I'm glad we're finally able to have access to this stuff.
Yeah.
It's about damn time. Okay. So,
well, let's throw one other reminder in there that we brought this up on the Swapcast, that Randall has no affiliation with Sacred Geometry International. He has not gotten paid anything for years from the sales or donations that are happening on that site. The administrator has more or less gone rogue and taken on everything for himself, seemingly believing that he owns it instead of Randall. So we're trying to steer everybody directly to randallcarlson.com for the products like Kyle was mentioning. Courses, newer versions of the Sacred Geometry courses are going to be coming soon. Randall's got a new studio coming together there in Atlanta, and those are going to be starting production. So hold off. Don't purchase from the older versions. There's new ones coming.
Thanks, Brad. Yeah,
that's right. Yep.
I'll second that. And
if you want to start playing, the compasses are available.
Oh yeah. Yeah. And we'll add that, yeah, the Sacred Geometry courses and classes that we're creating are definitely an upgrade from what's being sold, that were created 10 years ago and never finished and shouldn't have been sold in the first place until they were finished. But we won't get into that. Anyways, yeah, we got much more, a much greater upgrade coming.
Yeah, looking forward to that.
Yeah,
for sure.
And more hands-on classes.
Mm-hmm.
Yeah.
Yep.
In person, you can come.
Yeah, we had a lot of fun with that Sacred Geometry course in Sedona a few months ago.
Absolutely.
And Matt Lohmeyer was there, and he wrote in his now best-selling book, Irresistible Revolution, in the right in the second paragraph of the introduction, he talks about what a great impression that class had on him.
Nice.
If I had it in front of me, I would actually read it, but we might do that next week. Anyways, I want to get back to Yokalaups, outburst floods, glacial dams, so on and so forth. All right. So I have in front of me now a copy of Larry Gene Hansen's 1970 thesis that he wrote. And after going through the possible explanations for the origin of Moses Coulee. He gets to the page 63 of his thesis, the preferred interpretation. He says, a final and favored hypothesis requires the existence of a connection between the present Coulee head and the Columbia River to the north. So right there, the man who did more work than everybody else would quote if they're going to be talking about Moses Coulee. Of course, they're going to be quoting Larry Gene Hansen. And Larry Gene Hansen is saying right there, I'm going to pull up the map again. We'll do a share screen so that everybody can see what we're talking about. Here we go. Yes. The Columbia River to the north is what he's suggesting as a possible source for the water. So he's actually right there, 51 years ago, is looking for an alternative to Lake Missoula for the formation of Moses Coulee. He says the highest recognized elevation attained by the inferred floodwaters is 2,340 feet, recorded in the scour lines, and highest divide crossing along the south side of Burton Draw near its mouth. Except for the extreme northeastern margin, the surface of the northeast part of the Waterville Plateau lies below 2,340 feet elevation. So, assuming the major post-glacial deformation in the area and the volume of glacial erosion since the Coulee was cut has been less than a few tens of feet, then this plateau, and we're talking about all of this area here, right? This plateau right here was either flooded or ice covered during the highest discharge down Moses Coulee. For the flood surface to be maintained at this level, Grand Coulee could not have existed as a cross-plateau incision, which is exactly what I was saying. In other words, if the water is coming from the east, if Grand Coulee is here, it's going to deflect down, and it's not going to reach the head of Moses Coulee. But if we assume that there are sheet floods, subglacial sheet floods coming down from the north, and they become channelized as they approach the rim of the ice sheet, then we bypass the problems associated with trying to get the water from all the way over here in the Clark Fork Valley to over here, without having that water divert south through the Cheney-Palouse, south for the Telford, or south through Grand Coulee, if in fact the water creating Moses Coulee is coming from north, up here. So he is looking for alternatives. And he is looking for alternatives because he's just not making sense out of the idea that it's coming from far to the east out of Lake Missoula. So anyways, we can get into some more about this. But yeah, so this is, quoting from his unpublished thesis. So you heard it directly from the man himself, who's done the most extensive work on.
Did he later publish papers on that same work, or just in that thesis?
I think I've not seen any papers by him on this. And he is estimating here up to 350 million cubic feet per second coming through Moses Coulee, cutting Moses Coulee. He says, for comparison, the average discharge of the modern Columbia River at Grand Coulee is about 100,000 cubic feet per second. So if we go 350 million, divide by, what did I say, 100,000, then we're talking about that the flow that created Moses Coulee, Larry Gene Hansen is estimating here, could have been up to 3,500 times greater than the modern Columbia River as measured at Grand Coulee Dam. That would be an impressive flow. And then he says here, in concluding this section, he says, a possibility clearly exists, this is on page 60, that one or more ice-dammed lakes other than Lake Missoula served as the source of the Missoula Coulee floodwaters. The search for these possible sources, however, awaits further study. So here we are half a century later, studying this matter further and trying to come to some conclusions. Okay, so let's circle back to modern ice-dammed lakes and see what we can learn by looking at using the uniformitarian principle and looking at modern ice-dammed lakes and seeing if we can extrapolate 3 orders of magnitude up. So I will start by talking about ice-dammed lakes in Alaska. And in the journal, the Annals of the Association of American Geographers, back in September of 1963, was a paper, an article by Kirk Stone, geologist Kirk Stone, who's been studying glacial dammed lakes in Alaska. There are a lot of glacially ice-dammed lakes in Alaska. And in fact, the title of this paper is Alaskan Ice-Dammed Lakes. And this is what he goes into. In south central and southeastern Alaska is one of the world's major concentration of lakes dammed by glacial ice. There are 53 in an area about 800 miles long and 100 miles wide. However, until 1951, only the presence of some of these lakes was recorded in print, and a small number of them were known locally for irregular or periodic disappearance. The occurrence of an ice-dammed lake is the result of a combination of several regional characteristics in addition to local conditions of topography, supply of moisture and ice, and weather and climate. All of these require analysis. In general, it appears that the larger lakes have about the same characteristics of site as the smaller. But most of the larger lakes are known to empty and refill either regularly or irregularly. Important point here is when he's studying and learning about these lakes, he seems that the larger they are, the more regularly and periodically they're going to empty and then refill. He goes on to say of the 16 larger lakes, 11 are known to empty regularly or irregularly. This is possibly a distinguishing characteristic because signs of emptying were observed at 5 of the smaller lakes. The actual process of emptying is only partly known. It has been observed in detail at only Lake George and Tulsaquah Lake in general and at a few other Alaskan ice-dammed lakes during aerial observation or by the interpretation of air photos. In a preliminary report based on field work in 1951, all such drainage was noted to be, now get this, under the damming ice, most often by undercutting along the rock-ice contact for all of the distance to the end of the damming glacier.
Wow.
Yeah. Previous limited observations concurred, and additional evidence strengthens the conclusion that most of the world's ice-dammed lakes probably empty through sub or N-glacial channels. Sub, of course, meaning underneath the glaciers. N-glacial meaning within the glacier. N-glacial is spelled E-N-G-L-A-C-I-A-L. N-glacial, meaning within the ice mass itself. So he's saying that most of the world's ice-dammed lakes probably empty through sub or N-glacial channels, which is important to note, are part of a typical structure, glacial structure, particularly temperate glaciers. So let's go on. The mechanics of emptying are still subject to speculation. Probably there is more than one way. At Lake George, it was observed to be by subglacial movement of water along the rock-ice contact. At Tulsaquah, it is interpreted to be by lifting of the damming glacier's ice until old or new openings under or in the glacier are found. At only a few lakes are data on depths available, but it is probable that at many, the water is much below 9/10 the height of the barrier. Now, why would that be?
Because the ice is buoyant.
Because the ice is buoyant, yeah. It's just a little over 90% of the density of the water itself. So, yes, this is why it's buoyant. Further, it is known that the depths at the beginning of the Lake George outlet. Okay, now get this, the depth. Here's the depth now of this particular lake, which is a regular glacially dumping lake, as measured in 1951, was 114 feet. And at the lowest part of Tulsaquah Lake, which is, and interpreted depths from at other lakes, are much less than a proposed requirement of 150 to 200 meters. So 150 to 200 meters is a number that's being put out there as being the maximum depth at which ice is going to be able to retain water pressure. Now, 200 meters, let's go to the big one. 200 meters is going to be 656 feet. But what he's saying here is that theoretically, the maximum would be between 150 and 200 meters. But he's saying it is known that the depths at Lake George, the lowest part of Tulsaquah Lake, and interpreted depths of other lakes are much less. So in other words, in the real world, they don't get to that theoretical depth. They drain before they do.
Now, is this a function of, well, like either buoyancy or the pressure at the base against the ice?
That's exactly right, Kyle.
So it's able to push the water is able to force its way underneath at the transition between the ice and the bedrock.
That's exactly right. Study of the emptying of these and other ice-dammed lakes in the world has disclosed the probability of multiple mechanisms for emptying, which are dependent upon combinations of hydrostatic pressure, density and orientation of crevice patterns, slope characteristics of the beds of the lake and the damming ice, water temperatures, weather and climate, stability of the damming glacier, which of course is absolutely key, and reflection or radiation of solar or earth heat. 9 of the Alaskan ice-dammed lakes are known to have emptied more than once. 5 of them are larger lakes, which once emptied annually, and 3 still do. So now, let's back up for a minute and talk about the context here. Now, he's looking, this is a paper going back to 1951, right? Now, we've talked quite a bit about the Little Ice Age, and we're going to be coming back to the Little Ice Age because there's some amazing, important, and valuable stuff that we can learn from looking at the Little Ice Age and by looking at the medieval warm period that preceded the Little Ice Age. But here's a key fact about the Little Ice Age, which lasted essentially in 2 major phases, starting the first phase around roughly 1300, The second phase beginning in the later 1600s and ending in the mid-19th century. Okay, now, during these two phases of the Little Ice Age, one of the primary geomorphic characteristics was the massive expansion of glaciers worldwide. We're going to be talking about that because we're going to be talking about what happened to people living in villages when the glaciers, which had been receded for centuries, began growing and moving like a massive, wall of ice, and literally swallowed up their farms and villages, forcing them to basically relocate and then turn around and watch over the course of a few years the glaciers advancing, and like I said, pretty much destroying hundreds of farms and villages in the process. Okay, now it's been based on studies of the positions of terminal moraines, the greatest extent of the Little Ice Age glaciers can be measured. Well, it turns out that largely the Little Ice Age glaciers were the largest growth of glaciers throughout the entire Holocene. So let that sink in for a minute. Those glaciers got as big as they've been in 10 or 11 or 12,000 years since the end of the Great Ice Age. Now, mid-19th century, we start global warming. Basically, the climate starts warming up from the Little Ice Age, and what happens is that the glaciers begin to recede. Okay, when those glaciers are receding, of course, the recession is caused by melting. So as they're receding back and melting, what's happening? Water is discharging from the glaciers. Now, if you have the snout of a glacier and you have a gradient and the water is coming right off and can flow away, okay, that's one thing. But let's say you've got a valley, and let's say that valley is full of ice, glacial ice, and there are tributaries coming in from the sides. And now let's suppose that those tributaries, which are filled with glacial ice, they melt first. So now you have lakes ponded against the main trunk glacier. Now, that main glacier is also shrinking. So at some point in there, the water is pooling up, the ice is shrinking back. So simultaneously as the scale and pressures of the reservoir are increasing, the ability of the ice to retain that water ponded is decreasing. So at some point, that water can get under the ice, and that's usually how it happens. Gets under the ice and escapes and created a series of outburst floods. Other times you might have a valley glacier. The trunk glacier has receded back, but now the valley glaciers grow out and they grow across the main valley. So that's another way that Little Ice Age glacial recession produced, glacial meltwater lakes. So now you got this water that's in the main valley, and of course, as the main trunk glacier is receding back, it's melting, it's contributing water to the reservoir. So that reservoir is rising, and at some point, again, it pushes its way through the ice, usually through the ice and glacially, by finding some aperture, someplace it can get through the ice, or under the ice. Now, that going under the ice, it can be because there's a pre-existing tunnel there. There's a channel that the water can access, or it actually can temporarily lift the ice right off the substrate, allowing the water to get through. Now, of course, then once the water drains, the pressure goes down, and then if the ice mass is still there, it can settle back down onto the valley floor and then cause a resealing. And this is oftentimes how you get the annual recurrence. Now, you noticed that in that previous quote, it was talking about these dams, these larger lakes that periodically drain once a year. So basically what they're doing is that's one seasonal melting worth of water accumulation. And one season of melting is enough to overcome the ability of the ice to retain it. Okay? So let's go on here with with learning more about ice-dammed lakes. This is from 1971, Glacier-Dammed Lakes and Outburst Floods in Alaska by Austin Post and Lawrence R. Mayo. This was published in the Hydrologic Investigation Atlas, HA-455. And I'm sure you've probably read this several times, right, Kyle?
It's burned into the back of my mind.
Yeah, good. Published by the Department of the Interior, United States Geological Survey. Glaciers in Alaska cover an area of about 73,800 square kilometers, which works out to be 28,500 square miles. They're most highly concentrated along the Pacific coast and in the south-central part of the state. Many of these glaciers, as elsewhere in the world, flow across the mouths of adjoining valleys, right? Picture, and cause lakes to form behind the ice streams. These glacier ice dams are subject to repeated failure. It should be noted that large quantities of water can be stored in or under glaciers and may create serious floods even though no surface lake is visible. Such catastrophic floods have occurred in Iceland so frequently that the Icelandic term Jökulárlaup is now used internationally to describe them. Glacier-dammed lakes form in a number of different situations. The largest lakes, which present the greatest hazards, occur in ice-free tributary valleys blocked off by active valley glaciers. So that's just what we were talking about. Glacier-dammed lakes can be formed, change size, or be destroyed in so many ways in various geomorphic settings that a complete classification would be both cumbersome and of very little practical value. Once a depression is closed off by a glacier, it begins to fill with meltwater and rain runoff from the surrounding basin. The resulting lake continues to fill until the water overflows a bedrock saddle or initiates a self-dumping process at the ice dam. So I'm going to now pull up a share screen.
So the classification would have no value, and also it would really be a problem because then they'd have to define the type of ice dam that they're suggesting for Missoula.
Yeah.
I also find that interesting, just really interesting there that they mentioned that like you could have a stream, like you're saying, coming down one of these tributary valleys, hitting the main ice and just vanishing into it, but not coming out, but actually building up deep inside the ice there until it explodes. In other words, the whole process is completely hidden and you don't even know.
Right.
Until water explodes out of the front of the glacier. That's
until the water explodes out of the front of the glacier.
Wow.
Right.
Creating some tunnel valleys.
Yeah.
All right. This is Summit Lake, which is in British Columbia, filled to near maximum level in August of 1963. So this is a proglacial lake. Now, this is a black and white journal photograph, and I added a little color to it so you could see the lake. But this is a pretty beautiful picture in its own way because, look at the moraine material. Look at, this is what would be called a medial moraine.
So ordered. It's nice. Nicely ordered.
Yeah, it is beautiful.
Mm-hmm. Yeah. So here's Summit Lake in August 1970. The lake is drained through a subglacial channel. So lake is drained away.
Wow.
Here's Tiki Glacier, Canada. Photos taken in August 1965 as the glacier began to undergo a surge. So in other words, it goes like an order of magnitude or more faster than the normal progression of a glacier mass. It's usually, I think that the main idea is that the base becomes lubricated with water, which allows because if you take the water away, there's a lot more friction between the bottom of the ice and the ground. So it's going to move much slower. It's also going to depend on how fast you've got material accumulating. Now, if you follow this glacier up, somewhere up in here, would be the zone of accumulation. And then down below is the zone of ablation, where it's melting back. So typically, if a glacier is in equilibrium, it means it's melting, its snout is melting back at the same rate that it's accumulating up here. Now, thing to bear in mind again is glaciers are streams. They're slow-moving streams. So they're a whole integrated system, right? I like to think of the term, a living glacier, right? So there are movements that have been well documented, how a glacier flows. But a glacier is flowing, and as long as nothing interrupts that process, it will continue to flow. As long as it continues to accumulate up in the headlands, in the headward regions, melt away at the bottom. Now, if things warm up, let's say, and the melting accelerates faster than the accumulation, that means that the melting back, the recession of the glacier, is going at a faster pace than the forward flow is, the momentum of the forward flow. The opposite of that would be if something increases the amount of accumulation, which causes an acceleration of the flow, right? And then a glacier grows. Now, so there's this balance that goes on. And then there's the zone of equilibrium, or the line of equilibrium, where above that line, you're still in an area of ablation, and below that line, above it, you're in the zone of accumulation, and below that line, you're in the zone of ablation. And there are architectural characteristics of the glacier that shift right at that equilibrium line. But now, of course, here's the thing with temperate glaciers. Temperate glaciers typically have subglacial water. And it's the temperate glaciers that you will see water discharging vigorously from the snout. Right? Now, where is that water coming from? Well, that water is coming from basal melting, which can occur as a result of frictional heat. It can also occur as a result of geothermal heat. So that's one source of the water itself, is from the bottom of the glacier. The other source of the water is seasonal melting on the surface of the glacier, or rainfall on the surface of the glacier that percolates through the glacier and reaches the base of the glacier through moulins or crevices or fractures in the ice, you see. But in either case, a temperate glacier, one of the primary characteristics is that it has this layer of meltwater at its base. Now, apparently, sometimes when that meltwater gets copious enough and the pressure increases the pressure, like presumably if there's an influx of basal meltwater, the glacier can actually surge, and it can be going much faster, 10 times or even 100 times faster than its normal, say, annual rate of progression. So that's the thing about a temperate glacier. Now, when we talk about the glaciers up in Washington during the terminus of the Ice Age, during the latter part of the Ice Age, are we talking about, temperate glaciers, or are we talking about polar glaciers? Now, polar glaciers there's two primary categories. There's actually several categories beneath that. Like you have a polar glacier is one extreme, a temperate glacier is the other extreme. Then you have a subpolar glacier where you have some movement. A polar glacier, though, is frozen to the substrate. Well, and then the implication there is that there's little to no seasonal melting, right? Now, what that then implies is that you're not going to have rainfall, and clearly the formation of a great lake in the immediate vicinity of a polar glacier. Whereas you are going to have that, and that's what we repeatedly see in the case of a temperate glacier. So I don't see how it's possible to think in terms of any other kind of glacier for the Purcell Trench Lobe than a temperate glacier. I mean, the existence of Lake Missoula is clearly evidence that there's plenty of energy to melt either copious amounts of ice or to provide copious amounts of rainfall or snow melt. So we clearly can't we can have it one way or the other, but if the thing is we accept the existence of this lake, well, then we've got to assume that the general environment there is warm enough that we're not talking about a polar glacier frozen to the substrate. Because after all, I mean, if you have the water coming through 300, 400, 500, 700, or 800 million cubic feet per second coming out of the Clark Fork or down the Rathdrum Prairie, whatever ice is there, that's going to be gone. It's going to be completely swept out. So if you're going to impound another lake, that ice has to extend all the way back down through the Spokane Valley and terminate somewhere down by Spokane, somewhere down there, right? Now, if it's a polar glacier, well, it's going to be super slow moving. Now, but then again, where's the water coming from? You got to have a lot of water to fill a basin full 600 plus cubic miles of water. I mean, for an exercise, go outside and try to visualize an ice cube 1 mile on each side, a mile wide, a mile deep, and a mile high. It's a hell of a lot of water. Now multiply that by more than 600, and you got the volume of Lake Missoula, right? So this is a huge volume of water. Where did that come from? Is it rainfall? Is it snow melt? Is it glacial melt? And given that there's enough thermal energy to create this huge volume of water, then obviously it's got to be a temperate glacier. So a temperate glacier has copious amounts of basal meltwater. Now, in this current scenario, we got glacial Lake Missoula, 4,250 feet or so above sea level, 2,100 feet against the ice dam, at the heel of the ice dam. 30 miles away at the toe of the ice dam, we have glacial Lake Columbia lapping at the toe. And are you going to tell me now that 2,100 feet of water, which is going to make 950 some pounds of pressure per square inch, as we talked about last week, 950 times 144, yeah, that's 136,800 psi or pressure against 1 square foot per square foot, PSF. 136,800, call it 137,000 PSF. That's a lot of pounds to be against ice, glacial ice. Now, I read the quote last week from C. Warren Hunt talking about that this is an utterly frivolous idea to think that this is even possible. And I think even a modicum of rational thought would support that idea. Now, here's the same glacier. This is August 1965. Now, here's an example of where a tributary is forming a lake against a main valley glacier. Tiki Glacier in August of 1966 at the completion of the surge. So back up. Here's what's happening. The main valley glacier is surging, so it's moving fast. Now, normally, what's happening is you've got this small river wrapping around the front snout of the glacier, coming out of this valley, wrapping around. You can see the river actually is right in here. It's just a tiny little thing wrapping around, but now the glacier surges. It accelerates to maybe 10 or 100 times as fast as it normally is moving down valley. What then happens is that glacier comes south and it blocks off this tributary valley and accumulates 2 lakes against the ice. So now this is in August of 65. This is 1 year later. Okay? Note that it has blocked the 2 tributaries, causing them to form lakes. So what happened, of course, is that they drained. Glacier outburst floods from Hazard Lake, Utah, Yukon Territory, and the problem of flood magnitude prediction. For Hazard Lake and many other ice-dammed reservoirs, drainage ends when the lake basin is completely empty. So it is important to keep track of lake volume. A second reason for including reservoir geometry as part of the simulation model is that the pressure head at the tunnel inlet decreases as drainage progresses. This is an important point. Thus, the fluid potential gradient driving water along the tunnel decreases with time, as does the water pressure opposing creep or fracture closure of the tunnel. So this also applies to Lake Missoula, right? Because in Lake Missoula, as the water level is dropping, right, What's happening to the pressure head? It's dropping. What's happening to the energy that's driving the velocity of water out of this reservoir? Well, it's diminishing as well. Clearly, think about this. If you've got a depth of water and you've only got a narrow outlet, but there's a lot of pressure, think about the water is going to be shooting out of under pressure. Just like all you got to do, pick up a garden hose, and you put a pressure valve on the end of it, a spigot, right? All that's doing is, the water coming out of the garden hose will have a normal flow, but then you put on the valve on it, right? And you squeeze it. What's happening is it's decreasing the cross-section area, right? And what happens to the stream of water? Same thing in your adjustable shower. You turn the little nozzle and it'll focus that water and it increases the pressure. Now, figure you got a tunnel through the bottom of the glacier. The water is filling up. The deeper the water, the greater the pressure. As the water level falls, the pressure declines, right? So when the water is pushing its way through under pressure, it's generating heat from the friction. And then that friction enlarges the tunnel walls. And typically this is what happens. Now, this is one of the accepted mechanisms for drainage of ice-dammed lakes. There might be a small outlet. The water is moving through there. It finds its way through under tremendous pressure and then begins to enlarge the tunnel. And then at some point it reaches a threshold and the whole lake just drains suddenly and catastrophically. So the fluid potential gradient, that's the term, fluid potential gradient, driving water along the tunnel decreases with time, as does the water pressure opposing creep. Now, because once that water is quit flowing out, that ice, because it's flowing, it's going to creep together and you're going to have fracture closure. And this is the basic cross-section after Hazard Lake. So you can kind of see here. There we go. So this is Hazard Lake, Steel Glacier. This is in the Yukon, tunnel outlet. Now, in this case, the water is building up. We don't need to get into all of this. This is showing potential depth. Now, if you, of course, look at this at meter, what you're going to see here is that right at the ice dam lake interface, if you follow this line over, it's a little bit less than 500 meters. It looks like the tunnel inlet is right here right at 400. So you maybe have 70 or 80 meters there. So 80 meters is going to be, times 3.28. So that's going to be about 250, 260 foot of depth right there against the ice dam. And this is the depth at which this particular flood occurred. Hazard Lake then was able to force its way into the tunnel inlet, break the seal, and then flow under the glacier, and its outlet was at the southern snout. Now notice here the distance from the inlet to the outlet is from 0, so about 13 kilometers or about 8 miles. So this water had to travel about 8 miles in order to discharge from the tunnel outlet. Here's another periodically dumping water, ice dammed lake. So we don't necessarily need to go into all of this. It's showing here, look, ice surface in the mid-1800s. The ice has receded. There's a bedrock spillway. And here's basically the high water mark in 1961. And the water drained through the bottom of the lake. And here is the data on it. The depth of Strone Lake was 125 feet, 125 plus. So in other words, that's the high water. You see right here where the high water got, that would be the greatest pressure at the heel of the ice dam. Okay. That was just somewhat more than 125 feet. Notice that the volume of the lake, 4 times 10 to the 8 cubic feet, is 0.003 cubic miles. Now, let's just in round numbers use 600 cubic miles for Lake Missoula, and I will divide that by 0.003. And the difference between Strone Lake, when it burst through its ice dam, and Lake Missoula, well, Lake Missoula was about 200,000 times larger. Okay. Estimated average discharge, 2,500 to 5,000 cubic feet per second. Estimated peak discharge, approximately 15,000 cubic feet per second. Okay, well, let's try this. We go 800 million cubic feet per second, divide by 15,000, which was the maximum peak discharge of this outburst flood. And peak discharges of Glacial Lake Missoula were only about 53,000 times greater. So yes, it's a bit of an extrapolation. Here we've got another example, Summit Lake. Okay, let's see here. We've got Glacier Bed. We've got the Salmon Glacier. We can see here's the lake up here. Again, it drained beneath the ice and discharged down here. I'm not sure of the horizontal distance, but we've got the average depth at which the ice, the pressure of the lake was able to overcome the ice was 140 feet on average. Volume of the lake was 0.04 cubic miles. So we'll do the 600 cubic miles of Missoula. We'll divide that by 0.04. And in this case, Lake Missoula was a mere 15,000 times bigger. Total discharge time, 3 days. Average discharge time over 3 days, 20,000 cubic feet per second. Estimated peak discharge, 40,000 cubic feet per second. So we will just divide the peak discharge of Lake Missoula by 40,000, and we will see, the peak discharge of Lake Missoula was only 20,000 times greater. So, how many examples would we need? Here is drainage of Østre Oxtenbreen ice-dammed lake in Norway. 3 of the events occurred early in the summer, whilst melting of the winter's snow cover was contributing substantially to glacier river discharge. High basal water pressure and rapid sliding may have facilitated disruption of drainage conditions within the glacier. In 1982, the lake drained during a severe storm. In 1977 and 1984, shortly after a period of heavy rainfall. During the 1977 and 1984 events, water under pressure burst up through the glacier surface.
Oh, wow.
Yeah, burst up through. So, I mean...
Yeah, making geysers on the top of the ice, basically.
Yes, and showing that the water under pressure will overcome the ice.
Right.
And here is the drainage of that particular ice-dammed lake. Estimated peak discharge, though, was only 1,278 cubic feet per second. Lake Missoula approximately, here's the calculation, 12,000 times as large. Missoula peak flood discharge 626,000 times greater. So, I mean, we can go through looking at example after example after example of these ice-dammed lakes. And what we're going to see over and over again is the same deal. Typically, they get 100, 200, maybe in a few cases 300 feet deep. And the pressure gets great enough that they then overcome the stability of the ice. So this is interesting because in this particular outburst flood, look at all the moraine here, but notice the bridge and the tunnel.
Oh, yeah.
Yes. So we've seen natural bridge formed in up in Grand Coulee, which we know was created by catastrophic floods. This is created by the erosion of this outburst flood. So it shows that these turbulent waters can create natural bridges. So Russell Fiord, Hubbard Glacier outburst floods of 1986 and 2002. One of the most dramatic hydrologic events in the United States during this century occurred in May 1986 when the Hubbard Glacier, which originates in an ice field in the Canadian part of the St. Elias Mountains and flows in a southerly direction through the Wrangell St. Elias National Park into Disenchantment Bay, sealed the entrance to Russell Fiord in the Tongass National Forest near Yakutat, Alaska, and transformed the fjord into Russell Lake. So, as it says, during the past century, the glacier had been encroaching gradually on the fjord, and it had been predicted post in Mayo 1971 that about 1990 the fjord would be blocked by the advance of the Hubbard Glacier against the northern part of Gilbert Point. When this blockage did occur on May 29, 1986, Russell Fiord, now transformed into Russell Lake, filled rapidly, giving rise to the possibility that by 1987, the elevation of the lake would be so high that it would discharge into the Situk River Basin. If that were to happen, the new outlet at the southwestern shore of Russell Lake would seriously disrupt a world-renowned fish-spawning habitat, drown forests, inundated 2 roads, and flood a bush airstrip and numerous subsistence fishing camps. So on October 8, 1986, before this could occur, the Hubbard Glacier ice dam failed. So again, picture that they were afraid that the height of the water would get so high that it would actually flow over a low point to the opposite end, to the upstream side of the fjord, right? But the glacier failed. It rapidly discharging an estimated 1.3 cubic miles of lake water into Disenchantment Bay. The outburst flood maintained an hourly average discharge of 3,700,000 cubic feet per second. This outburst may have produced the greatest short-lived discharge of water in North America since glacial lake outbursts floods occurred at the end of the Pleistocene epoch. So 3,700,000. That's quite a flow. And I'm going to put back in my 800 million, and I'm going to divide it by 3,700,000. And what we see is that the discharge of Lake Missoula floods was still over 200 times greater than this. So,
did anyone capture any of this on film or with pictures or anything? It's in
okay. So here's Yakut Bay. Here's the glacier here, right? Here's Yakut Bay, pointing to the bay right here that it's talking about. See, let's see. The immediate threat of overflow of water from Russell Lake caused by the advance of Hubbard Glacier, North America's largest tidewater glacier, is over, according to reports from Dennis Trabant, a glaciologist with the U.S. Geological Survey. The trapped water in the 70-square-mile lake broke free to the ocean on August 14th in a spectacular, roiling, and chaotic 36 hours, making the torrential channel into the sea an extremely fast-moving and dangerous river full of large chunks of ice and debris. The rushing river created by the discharge was about 300 feet wide and 600 to 700 feet long. So here we go. This is May 20th, 2002, looking toward the mouth of Russell Fiord, as you can see up here, from above Disenchantment Bay, right, which is at the north end of Yakut, right? We go back to here. This is Disenchantment Bay right here, right? Here's the glacier. And you're actually going to see that where it sealed off and formed the dam was right here at the point of my right there.
Point. Yeah. All right.
Yeah, right in here. Okay, so that's this right here. Okay. Gilbert Point on the right and Hubbard Glacier on the left. A fjord is an arm of the sea reaching into a mountain valley that was filled by a glacier during the Great Ice Age, but has since been drowned by post-glacial sea level rise. Note the width of the channel between the cliff face and the glacier face. With an open channel, Russell Fiord has a surface elevation equal to sea level, right? Because it's connected with the sea. All right. So here we go. Let's get this out of the way. Russell. So now this is August 25th, 2002. Let's back up. This is May 20th of 2002. August 25th of 2002. Hubbard Glacier. So now, of course, Russell Fiord is being fed by rivers and streams, right? And then, but then it's maintaining equilibrium because it got unimpeded contact. Because this is when you get in Disenchantment Bay, now you're out in the ocean, basically, right? You're in the sea. So here's June 14th, 2002, same view as the first slide. So this is August 25th. So now here's June 14th, 2002, same view as the first slide. Hubbard Glacier is encroaching upon Gilbert Point. Notice how the glacier is piling up moraine at its snout. See the moraine here? Yep, there it is. So here's June 16th. So 14th, here's 2 days later. Note the floating icebergs. See them down here? Look at this, floating icebergs. And the truncation of the cliff opposite the outflow channel, the result of former outburst floods. See this? You can see a high water or high glacial line right here. And now look at the moraine. This is all being shoveled, bulldozed ahead of the advancing glacier. And notice how it's forming whitewater here. Well, that's because if you were to measure the flow here, and the flow here, and the flow here, it's basically going to be the same. So it's flowing slower. When it gets into the constriction, it has to speed up. Well, of course, as it speeds up, it becomes more erosive, doesn't it? Okay, so here's June 20th. So here's June 16th. Here's 4 days later. Look at what's happening to the channel. And look at all of the floating ice.
Yeah. Wow.
Here's June 23rd. So here's 3 days later. The advance of the glacier is pushing the moraine pile towards the cliff face on Gilbert Point. And notice now also how the icebergs and so forth are becoming jammed.
Yep, they're backing up in there. Yep.
Choking up. Yep, exactly. Exactly. And notice how chunks of ice are scattered on top of the moraine.
Yeah.
Yeah, and look at how much ice debris is floating in the water here.
Yeah.
June 28th. Notice that the moraine is now shoved right up to the cliff face, and flow blockage is beginning to occur in the outlet channel.
God, look at that glacier back there.
I know.
Good grief.
Pretty. Yeah. Okay, so we go from June 28th. This is also June 28th. The narrowing of Russell Fiord's outlet channel is readily apparent in this photograph.
Yeah.
And look how much, ice debris you have floating in the water now. Because look, as the water is coming through here, of course, what's happening is that the ice here jams up in the opening, but then what that does is increases the pressure on the upstream side of that ice jam, doesn't it? So then it's pushing this stuff through. But at the same time, this glacier is advancing and pushing up this moraine against the cliff face. I mean, this would have been something to witness, this whole thing, man.
Oh, yeah.
Okay, back to June 28th, July 3rd. Okay, so look how narrow the channel is now. Look at the moraine here. As it says, note the texture of the moraine.
That's crazy.
Yeah.
July 11th.
Yep.
July 16th.
It's
almost completely
white water there. Yeah,
right. Yeah,
it's channelizing between the moraine and the cliff. You can't even see it.
Yep.
right. It's pretty much at the final stages of being sealed off. So then what happens as soon as that starts sealing off? Water starts accumulating up here. And Russell Fiord becomes Russell Lake. And then the depth of the lake increases. Here we go. July 21st, the moraine is almost in contact with the cliff face, blocking the channel between the Fiord and the bay. Bay down here, Fiord up here. And of course, you can see this huge mass of icebergs jammed in up here. And we can see now this is what I'm arguing. This would have been sort of a scale invariant representation of what I think happened at Wallula Gap.
Oh, yeah. Haven't seen that yet.
Wallula Gap?
Yeah.
Well, that'll be the September trip.
Next time.
That's right.
August 2nd. So this is like at the lower end of the fjord. August 10th. And then this, August 14th. From this
breaks through
to this.
Wow.
Yeah.
Just,
So look, all you see is a remnant.
Yeah.
Only a remnant of the moraine pile exists.
Yeah.
Now that would be a trip to raft or canoe or kayak through this.
Yeah.
So we go August 14th. Yeah. So here's August 14th. The moraine is now completely washed away. Look at the sheer ice walls here.
And just carved that ice flat.
Yeah.
Score. Water wins again.
That's right. Water always wins.
Water wins. August 14th. Now that's some serious turbulence there. Now I want you to look at the ice.
Yeah, look at how fractured it is. It's like,
yeah,
doesn't look like good dam material.
Right.
You know what I'm saying?
No, it doesn't really look too like, it would be the most effective dam material out there. Yeah.
Yeah. Yeah, the moraine was better. I mean, it was at least consolidated but still, it just shoved it out of its way.
Well, of course, see, with the constriction, the water level rose in Russell Lake
until it overflowed
until it burst its way through, and now by August 15th, equilibrium has been restored.
Yeah.
The catastrophe
is over. Does this
is
just keep happening over and over?
Yeah, I was going to say, is this still a problem?
Well, it's happened at least twice that we know of. But see, here's the thing. Again, remember how I explained how the glaciers expanded to their largest extent?
Yeah. Yep.
Well, as they've been receding throughout the 20th century, the ice dams and the outburst floods have also been receding in magnitude.
Okay.
Russell Fiord has returned to the sea. So we'll end with this last one here, which is from 1987, Geological Society of America Bulletin, a depositional model for outwash sediment sources and hydrologic characteristics of the Malaspina Glacier, Alaska, a modern analog of the southwest margin of the Laurentide ice sheet. And this is what he says. Meltwater enters the Malaspina Glacier via, notice the number of routes that it has, intercrystalline spaces, moulins, which are fractures that basically go to bedrock, crevices or sinkholes, and moves down glacier through a system of end-glacial and subglacial tunnels. Now, that's what we see in the case of temperate glaciers. Think about that. Intercrystalline spaces, moulins, crevices, sinkholes, down glacier, water moving down glacier through a system of end-glacial and subglacial tunnels. Stratified sediment preserved in these tunnels indicates that meltwater erodes the bed of the glacier. Meltwater exits the glacier as fountains or from open tunnels to form outwash plains, or from end glacial or subglacial tunnels that discharge into ice marginal lakes. These characteristics of the Malaspina are shared by many temperate glaciers. So think about all of that. Intercrystalline spaces, moulins, crevices, etc. Just like you said, Russ, how effective is temperate glacier ice going to be as far as impounding water, meltwater? Well, we've looked at a few examples. We saw the example of the biggest flood, what they're saying perhaps in North America since the end of the last ice age, the thing we just looked at, the Hubbard Glacier, right? We looked at it, had 3,700,000, but look how quickly the lake formed and then was destroyed. It certainly didn't get 2,000 feet deep.
Nope, not even close.
So I think that it's a fair question to challenge this ice dam model and to say, no, I don't think we can extrapolate up 3 orders of magnitude minimum from modern ice dam lakes, because I think what modern ice dam lakes teach us, and we only got into a little part of it, we're going to look into some more really cool stuff next week.
Excellent.
But yeah, what have we seen here? We've seen that, bodies of water that are minuscule compared to glacial Lake Missoula are perfectly capable of penetrating through their ice dams and discharging and draining away. And they'll do that repeatedly and periodically, oftentimes, sometimes even annually.
On an annual basis, right?
Yeah. So what does that say about the efficacy of glacial ice to retain water to any significant?
For hundreds of years, or 50 to 100 years, like Missoula is supposed to have done multiple times.
Yes.
Yeah.
Yes. So, that's, I think there are legitimate questions that can be asked here.
Yep. Well, Brad's got his hat on. Kronos, it's time to wrap it up here.
Yep. Well, I'm ready.
Okay. Well, everybody can check randallcarlson.com for all the podcast details about the trips, details about stuff that Randall's got for sale, including probably information about things that are upcoming.
Mm-hmm.
So, yeah, but basically for everything Randall and everything about the podcast, randallcarlson.com is where you go. There's also places there to get in touch with the team for various reasons, right? Isn't there Brad, there's if
form. Anybody wants to complain about anything, you contact Russ.
No. False.
Just kidding. No, that's what we got Normal Guy for.
Yeah, there you go. Contact Mike.
Yeah.
Yeah, there it is.
Sure.
He's the complaints
Contact
department.
Norm. Well, Mike, good to see you. I'm glad you're doing well.
Thank you. Thank you. Good to be here.
Good.
Yep.
And that's a nice T-shirt. By the way, those T-shirts, Kosmographia T-shirts, they're available.
That's right.
In
many colors.
Sizes and colors. Check it out. It's on the way. Oh, and the hats, too. I need to be wearing my hat.
Yeah.
Yeah.
Cosmo
Show your
cap.
support. Get yourself
That's
a
yours.
T-shirt. They're nice. They're actually very comfortable T-shirts.
They are. They're very nice.
Send us pictures.
Yep.
Yep. One of these days, we're going to have a show and tell.
There you go.
Okay.
All
If
right.
you wear one
Good
of the
stuff.
pyramids, to send us a photo.
Yeah. For sure.
Only from the top, though.
Anything else, Brad, before we wrap it?
Time to go.
Okay. Intercrystalline Spaces. Fantastic band
name.
Yeah.
Man.
I knew it as soon
Hey.
as I saw it. You do a trip rock band. Intercrystalline Spaces, right? All right, guys. Great show. Good night.
night.
Next
Good
week.
night.
See ya.
Good night, guys.
Yeah.
Right. Ciao.